Okay, so let's discuss about the question and answers in Terpenoids. Okay, previously we discussed a few questions. Today also we will discuss a few question and answers. Uh, Maybe you know that complete the following reaction. It's a beta carotene when it is treated with aqueous K metaphor. You're supposed to get beta ion. So this beta ion on ozonolysis gives gyrenic acid. Okay, so beta carotene. 1 minute, I will make an entry. Okay, so complete the following reaction. It's a 2 marks question. So you have to write, you can write the beta carotene or you just write the formula, molecular formula of beta carotene. And when it is treated with 1 minute. Okay. So you can write the molecular formula and when it is treated with KMNO4, it gives beta ion. So this beta ion on treating with ozonolysis gives what is called as gyrenic acid. And you have to write the possible, I think four structures are possible for the farnesol. Cis, what you call cis, trans cis. Okay, four possible. You have to write that. And what happens when alpha phenene is oxidized with alkaline KMNO4? So it's what is called as cyclobutane, dimethyl cyclobutane dicarboxylic acid is product. How is obtained that you have to write here, but don't write the product itself, but you have to start with the alpha phenene. So you can start with the what is called as molecular formula, or you can also write in terms of structural formula itself. And caryophyllene hydrogenated means since it contains two double bond, it will consume 2 mole of hydrogen forming a saturated one. So that you have to mention. Then gibberellic acid on hydrolysis gives dicarboxylic acid. See here, gibberellic acid on hydrolysis, it will give you two product. That's what is called as hapo gibberellic acid and gibberic acid. Two products formation you have to explain here. And a Namekin rearrangement in campaign. So that means a migration of methyl group 1,2 shift is called Namekin rearrangement. So just mentioning the 1,2 shift of methyl group is called Namekin means teachers won't accept that, but you have to take an example and you have to write that. So, with all these questions and answers, I will explain in the next slides. So, this is the question I'm taking. So, complete the following. 1 minute. I will make you an entry. Right. So, complete the following reaction. It's a 2 marks question. Beta carotene when it is treated with aqueous K metaphor. Here the product is beta ion, and beta ion when it is treated with ozonolysis gives gyrenic acid. So that is explained in the next slide. So that is this. So this is a beta carotene. Beta carotene when it is treated with cold KMNO4 in benzene, it gives beta ionone. So this beta ion, when it is treated with ozonolysis, gives an intermediate like this, and then finally it will give you gyrenic acid. It is for the 2 marks question. So if you are writing beta ion, 1 marks. If you are writing gyrenic acid, that will be another marks. Okay, it's a continuous. Maybe you can make an arrow mark from here to here also, no problem. So this is about what happens when beta carotene is treated with KMNO4 and obtained one is treated with ozone. So with this, I will go to the next question is the draw all possible stereochemical structure of farnesol. So stereochemical structures of farnesol means this is the structure of farnesol, and more particularly here I am written a what is called as a linear structure of farnesol, and you have to numbering should be starting with this carbon because this is the functional group. So 1, 2. So that means at the second position there is a double bond. Similarly, at the sixth position there is a double bond. And this double bond does not exhibit geometrical isomerism, but these two exhibits diametrical isomerism. And to this double bond, this group is a priority group. This is the priority group. So both the priority groups are on opposite side. So it is a trans. Okay, trans is represented as E. Similarly, this double bond, this is the priority, this is the priority. Both the priorities are on the opposite side, so it is a E. So this is the EE farnesol. Otherwise, what we can say that trans farnesol. And this is one more same thing only, but here this double bond is instead of writing methyl group there, it is written in the down. So thereby this double bond is converted into a cis one. So that means 2 cis 6 both the things is Z. Okay, this also both the priority groups are on the same side. So both the Z. This is Z. This also a Z. That means 2Z, 6Z. So cis is farnesol. And here, so 2E. 2E means trans, and 6Z. 6Z means it's a cis because both the priority groups are on the same side. Here the priority groups are on the opposite side. So it is called as trans cis farnesol. And this one 2Z, that means both the priority groups are on the same side, so it is a cis one. And this one is trans one, so it is a cis trans farnesol. So you need to write all these four uh, uh, isomers, possible isomers for the farnesol. So with this I will go to the next question. So next question, what happens when alpha pinene is oxidized with alkaline KMNO4? It is for 2 marks question only, but you have to write all these things. So I am taken in terms of molecular formula. You can also take in terms of structure. So alpha pinene, when it is treated with alkaline KMNO4, it gives pinene glycol, and this pinene glycol on warm with KMNO4 gives pinoic acid. It's a ketocarboxylic acid. So this ketocarboxylic acid and treatment with sodium hypobromide. So methyl ketone, if methyl ketone is there means it will go out as a chloroform or bromoform. So obtained dicarboxylic acid on bromination. So alpha position of the carboxylic group is brominated. When it is treated with barium hydroxide, it undergoes dehydrohalogenation, means formation of double bond. And that double bond is when it is treated with uh, lead oxide. Lead oxide is an oxidizing agent. Okay. So what is the product obtained? The obtained product is having a molecular formula C8H12O4, and name of this compound is cis-nar-pinic acid. So nar means one carbon atom less. So and qualitative analysis, it shows a dicarboxylic acid. So when it is a dicarboxylic acid means you have to remove CO2H twice, CO2H twice. And it is also found that it is having a dimethyl group. So 2-dimethyl is removed. Then the leftover thing is C4H4. So C4H4 is this. So, and one more thing, you have to, here I am written as a cis. Okay, cis means this both the carboxylic groups are on the same side. This cis, again, you know that suppose one carboxylic acid is towards the observer, another is away from the observer, then it is trans. And if this carboxylic acid and this carboxylic acid both are away from the observer, then it is cis. If this carboxylic acid and this carboxylic acid as both are towards the observer, then also it is cis. So one is away, another one is towards means then only it is trans. So this exhibits two geometrical stereo isomer. So I will give an entry to one of your friend. Okay. Then so this is about that means cyclobutane, dimethyl cyclobutane dicarboxylic acid is the product when an alpha pinene is treated with alkaline KM-4. Okay, of course. So then what you can write, maybe you can write up to this, because up to this only KMNO4. From here it's sodium hypobromide. Okay, so maybe up to this you write. Maybe if you want to write in terms of structure, you can also write in terms of structure up to ketocarboxylic acid formation. So with this I will go to the next question. So give Namekin rearrangement of campaign. Okay. So you have to take a campaign. This is the campaign. And this campaign, when it is treated with HCl, okay, proton H plus and Cl minus. So proton will add to less substituted one and anion part will add to more substituted one. I think you are aware about the Marconi cap addition. So, is it follows a Marconi of addition or anti-Marconi of addition? So you know that anion part, if it is attacking a more substituted one, so that is the product is obtained here. So then afterwards, what will happen? This Cl minus, since it is a living group, and one more thing, this Cl is attached to a tertiary carbon atom. So that is the reason the tendency of living group nature of chloride is more because it is attached to tertiary carbon atom. And the obtained one is a tertiary carbocation. So that is stabilized by resonance. So what is happening? There will be a migration of this methyl group from here to here and this Cl is going out. So once methyl group is moved from here, there will be a positive charge formation on this carbon atom. So when there is a formation of positive charge on this carbon, so that time Cl minus is attacking. So that is how the product is obtained. So at this time, there is a removal of proton from this methyl group and forming a isomerized product. So you can say that this as well as this campaign is isomerized ones. Okay, so this is what the Namekin rearrangement. So main Namekin rearrangement only the 1,2 shift. Okay, methyl group. Okay, more particularly Cl will go out. This will attack here. So this is only Namekin rearrangement. But you have, so since there is a mention the campaign, so you need to write all these things. So with this, I will go for a next slide. So next slide, give the difference between alpha, beta, gamma carotenes. Okay, I think this is not the question. Actually, this is not a carotene. This is a caryophyllene. So the question itself I have to remove. Okay. Give the difference between alpha, okay, beta and gamma. It's correct, no? Alpha, beta, gamma, caryophyllene. Okay, so it's a 2 marks question. Give the difference between alpha, beta, gamma, caryophyllene. So you know that this is the alpha caryophyllene. It's a means monocyclic compound, and it contains 3 double bonds. And this one is beta caryophyllene, and it is having a 2 double bonds. One is exocyclic double bond, another one is uh, intracyclic, but the double bond present in a 9-membered ring. And beta carotene is a bicyclic compound. So one is 4-membered, another one is 9-membered. So gamma caryophyllene, it is also a bicyclic. Of course, there is a uh, what is called as a exocyclic double bond and intracyclic double bond. But what is the difference between the beta and gamma? So that you have to explain. So the difference between the beta caryophyllene and gamma caryophyllene. So beta caryophyllene is a what is called as a trans isomer. So whereas gamma caryophyllene is a cis isomer. And when we are talking about the trans and cis, when we are talking about the geometrical isomerism, this particular double bond does not exhibit the geometrical isomerism. Only this double bond exhibit geometrical isomerism. So because attached groups are different, but here the attached groups are same. So here you can observe that the priority group, this is the priority group, this is the priority group. So priority groups are on the same side. That is the reason it is a cis one. Gamma is the cis one, beta is the trans one. So that is the difference you have to mention. So if you want to mention about the difference between alpha, beta and gamma caryophyllene, you have to say that alpha caryophyllene is a monocyclic terpenoid, and it is having a 3 double bond. Beta caryophyllene is a bicyclic terpenoid, and it is having a trans double bond in it. And gamma caryophyllene is a bicyclic terpenoid, and it is having a cis configuration. So this is what the difference you need to mention. So with this, I will go for a next slide. So next is about how do you convert santonin. Okay, this is the santonin into desmotroposantonin. So that means this one, desmotroposantonin and the santonic acid. Okay, of course this is a santonous, but just I take this draw to show that how the santonin is converted into desmotroposantonin. And just to show the difference between the santonin and the desmotroposantonin. So the santonin on treating with HCl, it's converted into desmotroposantonin. So you know that the first ring here, this is not aromatized, but this one is aromatized. So that is the only difference. Also other things are same. So that's what need to mention here. And sand, of course, when this is treated with HA in presence of phosphorus, how it will form, you know that there will be a migration. This methyl group is migrated from this carbon to this carbon. Okay, here also you can observe that when it is treated with the HCl also, there is a migration of this bridged methyl group. This is called bridged methyl group, or one more word we can use for this methyl group, it's called angular methyl group. So it's better, let us use the terminology called angular methyl group. angular methyl group is migrated from bridged carbon to this carbon, and the ring A is aromatized. That's what the difference between the desmotropo santonin and santonin. And santonin is gets converted into santonin in presence of HCl by involving the migration of methyl angular methyl group, okay, forming ring A as the aromatic. And also, what you can say about angular methyl group is also moved from here to here. So in addition to that, there is a here there is a loss of water molecule, and thereby leads to a formation of double bond. So that is the xanthonous acid. Okay, of course, maybe one more thing you can find in the notes, that is how the santonin is converted into santonic acid, that you can write in addition to this explanation. So with this, I will go for a next slide. So next slide, I am taking alpha santonin itself. So it is asked for the 2 marks question. So what you need to do, sketch the mode of union. Okay, sketch the mode of union isoprene units to form alpha santonin. So this is a alpha santonin. So here what you need to do, you need to identify the isoprene units present in this uh, santonin. So maybe you can consider, you can start with this carbon, 1, 2, 3, 4, 5. Up to this carbon is one isoprene units. So from this carbon onwards, it's a 1, 2, 3, 4, 5. Up to this carbon means up to this carbon another isoprene units. Then this 1, 2, 3, okay, and then this one is 4 and this one is 5. Up to this is another isoprene units. So if you want to say about the head and tail fashion, so this part is head, this part is tail. This part is head, this part is tail. And this part is head, this part is tail. So this is how you can identify. So but you have to mark it. Here you can mark it one line like this and say that one isoprene unit, and you make a one line here and say that one more isoprene unit, and from here one more isoprene units, that you have to write it on the structure, and also you have to say that head and tail portion. So this part is head, this part is tail, this part is head, this part is tail, this part gibberellic acid. So this gibberellic acid on hydrolysis gives two products. One is gibberic acid, another one is halogibberic acid. So what is the difference here? So you know that what is that a lactone? Okay, lactone is hydrolyzed. So when lactone is hydrolyzed, and also in addition to the hydrolysis, the ring A, okay, ring A is converted into aromatic moiety. So you can observe that this is aromatic, this also a aromatic. And what is the difference? Here the hydroxy group is there, that will go out as a water. Okay, and lactone is there, that is also hydrolyzed. So then what is the difference between the gibberic acid and halogibberic acid? So gibberic acid and halogibberic acid, the ring A is same. Of course, ring B also same, but there is a difference in ring C and ring D. So in the ring C, a methyl group is attached in gibberic acid. In halogibberic acid, ring D, a hydroxy group is attached. In gibberic acid, ring D is ketone is there, and in halogibberic acid, ring D, a CH2 group is there. Means exocyclic double bond is there. So that is this is what you need to explain. So you need to explain that gibberellic acid and hydrolysis gives gibberic acid and halogibberic acid. That's what you can mention. If you are writing in terms of structure, that's also fine. If you are writing in terms of words, then it depends on the valuer right. So this part need not to be right. Okay, if you are writing, it's fine. So it's actually this is not required. A gibberine formation is not required because it is only concerned to the hydrolysis one. So with this, I will go to the next slide. So next I'm taking the difference between the alpha, beta, gamma carotenes. Okay, so this is alpha carotene, this one is beta carotene, and this one is gamma carotene. So what is the difference you can observe? So you know that alpha carotene is a optically active, more particularly chiral compound. It contains one chiral carbon atom. So that is the speciality about alpha carotene. And what is another? The absorbance is around 454 nanometer. So that is another one. And alpha carotene is showing a violet color. So that is one more. And beta carotene, it is optically inactive because it does not contain, of course. So all these alpha, beta, gamma are exhibits stereoisomer because of the geometrical double bond is there, no, because of the many double bonds are there. Okay, how many double bonds are there? You can observe that. So look here. So it should 11, no? There should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, 11 are there. So if we are not taking this double bond and this double bond, then there are 9 what is geometrical isomer exhibiting double bonds. Okay, but whereas in the case of yes, here in the gamma, there should be a addition one more. So 10 double bonds exhibits geometrical isomers in gamma carotene. Okay, so with respect to the difference between alpha, beta, gamma, so if you are mentioning the structure or if you are writing that alpha carotene is having one chiral carbon atom, and it is violet in color and the absorbance is 454, and beta carotene is the does not contain chiral carbon atom, the absorbance is 464 and it is a red colored one, and gamma carotene it is having monocyclic. Okay, these two are bicyclic, but this is only the monocyclic one, and it is of course it is absorbance is 474 and it is a dark red color one. So this difference you can mention for the 2 marks question. So with this, I will take up a few more questions. Uh, Sketch the mode of union of isoprene units in alpha santonin. So that this question I have discussed. Give the difference between alpha, beta, gamma carotene. So this also I have discussed. Give the steps involved in the cyclization of squalene into a alpha lanosterol. Okay, so here what is the cyclization of squalene? I think you know that squalene. So I will go back to the conversion of squalene to lanosterol. Okay, I will just move the slides to the backward direction. Maybe I will do like this. Okay, this is the one. Okay, you know that this is the squalene, and this squalene, how it is converted into lanosterol. Lanosterol is a sterol. Sterol functional group means gonane, means a 5-member what is called cyclopentano phenanthrene. Okay, per hydro. Per hydro means there is no double bond. So per hydro cyclopentano phenanthrene skeleton is called gonane system. So this gonane system is having a basic structure for sterols. Again, sterols are the naturally occurring one, and this squalene is converted into lanosterol. So how this is converted? Maybe you can, first you have to write a structure in this format. Then when this is treated with NADP plus, NADP plus is the one uh, what is called anaerobic oxidizing agent. So what will happen? There will be addition of oxygen to this double bond, terminal double bond. Okay. So this terminal double bond gets converted into epoxide. So once the terminal double bond is converted into epoxide, then there will be a cyclization. How the cyclization? This double bond attack this carbon. At that time, this one picks up a proton. So then what it means? There will be a one 6-membered ring formation between, there will be a new bond formation between this carbon and this carbon. So there is a positive charge on this carbon. So that time there will be a new bond formation between this carbon and this carbon. So then there is a new positive charge formation on this carbon. So that time there will be a new bond formation between this carbon and this carbon. So that time there will be a formation of positive charge on this carbon. So that time there will be a new bond formation between this carbon and this carbon. So leaving behind the formation of carbocation on this carbon. So that is how a intermediate is obtained like this. So at this moment there will be a migration. So migration of adjacent groups. So since there is a positive charge here, there will be a shift of hydrogen. Hydrogen is shift from this carbon atom to this carbon. 1-2 shift of hydrogen. So then there will be a formation of positive charge here. So that time adjacent, this hydrogen is shift from here to here. So then there is a formation of positive charge on this carbon. So that time there will be a migration of this methyl group to here. Then there is a formation of positive charge on this carbon atom. So that time a methyl group is moved from here to here. So then there is a formation of positive charge on this carbon. At this stage, there will be a loss of proton. So that means this bond pair is coming over here. This proton will go out and forming a lanosterol. So this is how lanosterol is obtained, and this is how lanosterol is obtained by the conversion of squalene. Okay, this is about conversion of squalene to lanosterol. So now I will go for a one more question. I will go back to the question section. So this is the one. Okay, this is over, and cyclization, this is also over. So define isoprene rule identify the isoprene unit in menthol. So what you need to do, define isoprene rule means you have to say that all naturally occurring terpenoids on heating gives isoprene units. Okay, that is isoprene rule, and you have to write the structure of menthol. Okay, so in that structure of menthol, you have to identify the two isoprene units. Okay, because what is that? Menthol is a monoterpenoid, so that means it is obtained by the combination of two isoprene units, and you have to write the what is head portion of the isoprene unit, what is tail portion of the isoprene units, that you have to identify. So then give the steps involved in the biosynthesis of abiotic acid. So abiotic acid, so it is a biosynthesis. So biosynthesis means abiotic acid. Okay, I will go back to the biosynthesis of abiotic acid. Okay, so this is the one, biosynthesis of abiotic acid. So this is the structure of abiotic acid. So this is obtained by the combination of farnesyl pyrophosphate. Okay, this is how abiotic acid biosynthetically synthesized in living system. So farnesyl pyrophosphate react with isoprenyl pyrophosphate. So what is happening here? The base part of the enzyme can abstract this proton, and this bond pair can come over here, and this bond pair attacks this carbon, and OPP means pyrophosphoric acid moiety will go out as a living group, forming a linear structure like this. So this linear structure we can convert it into a this form. So you can what is this dimethyl's double bond. So that is the one, and two s saturated carbon atom. So two saturated carbon atom, and double methyl and double bond. So methyl and double bond. So afterwards, two saturated carbon atoms, that is these two, and methyl double bond. So methyl double bond, and two saturated carbon atom, these two, and methyl double bond, and CH2 OPP. So here now there is a cyclization. So cyclization means there will be a new bond formation between this carbon and this carbon. So that means it is converting into a six-membered ring. And similarly, there will be a new bond formation between this carbon and this carbon. So that means another six-membered ring formation. And the remaining CH2, this CH2, and this CH3 is this, and double bond is this, CH double bond is this, CH2 is this, OPP is this one. So at this time, again it undergoes cyclization, forming another six-membered ring. How means there will be a new bond formation between this carbon and this carbon. Okay, so that time this double bond is going over here, and OPP will go out. So that is how a compound is obtained by the formation of this one. Since there is a involvement of this bond pair in new bond formation, so this carbon attains a positive charge. That's what I have written here. So at this stage, there will be a removal of this proton, and the movement of this bonded pair to here. So there will be a double bond formation. So this proton, when it is going out, this proton is captured positive charge on this carbon. Since there is a positive charge on the secondary carbon atom, this methyl group is moved from this carbon to this carbon, forming a isopropyl substituent. So now there is a positive charge on this carbon. At this moment, the base part of the enzyme can abstract this proton, and this bond pair is coming over here. This bond pair is come to this. So there is a formation of compound like this. So in 3 steps, okay, or 3 or 4 steps, it is possible to convert this intermediate into abiotic acid. So what is the difference between this and this? Only this carbon should get converted into carboxylic acid. So this maybe involves the carboxylation. I think you are aware about the vitamin B12, cyanocobalamin, may be involved in the conversion of this CH3 group into carboxylic acid. So this is how abiotic acid is synthesized uh, um, in bio. So I will look for a few more questions. So the remaining questions I campaign. It's a direct question that you can look into the notes. Okay, maybe what I will do, I will stop at this stage, and I will continue in the next class. Means tomorrow's class, I will discuss a few more questions, and afterwards, if possible, I will take one more chapter in medicinal chemistry. Okay, maybe now uh, I will maybe now I will stop sharing, and you can also log out. If you have any doubts, you can ask.